Okay, thanks for coming back. So I just mentioned a bunch of study about how to analyze in the word embedding and then extended to embedding beyond English and bilingual embedding. So people may already have a question in the mind that how about contextualized embedding, right? Because we know nowadays people not only trying to train a factor for each word, but also trying to capture the context in the sentence. So there is a study by Jerry in the NACO 2019 that trying to analyze how the gender is embedded in this contextualized embedding space. And this is done with Elmo. So I am not sure if the result hold for bird or not, but this basically shows you some interesting things. So what she did is that we generate a pair of a sentence, and again, just swapping the pronoun from she to he or he to she, and we're trying to see how the model embed this kind of a gender information in this contextualized embedding space. So more specifically, we have a sentence like I show you here. So there is a gender pronoun give you the hint that this driver is a male or the female. And we're trying to see that by the contextualized embedding of a driver, we're trying to see that what kind of a gender information is there. So one interesting thing is that if we do the similar analysis that like the Newry's paper on word embedding, and you're trying to run the PCA on a bunch of this kind of a word pair, now the gender component is not only one component, but you can see there's like two top eigenvalue that kind of indicate that there are two kind of gender components captured there. So if you look at the progression of those words in these two dimensions, then you will find that one dimension basically capture the implicit association of the occupation word to the gender, and the other dimension capture these he or she in the same sentence. So this is nothing special, nothing surprise, but we also trying to analyze if there is a gender bias under this context. So what we did is that if I give you this contextualized embedding of the word like driver, and can we predict what is a gender word in the same sentence? So if there is no bias there, then you would imagine the model can make the similar high performance predicting that there is a he or she in the same sentence. But the result is not like that. So if we have the occupation word that is still typical to the gender pronoun in the same sentence, then the model actually can predict this much better than the other way around. So and also you can see that basically the male information, if you want to make this prediction, the model is more easily to predict there is a male in the same sentence than the female. So that basically captures certain bias in the data. Okay, so why that is a problem, right? And the problem is that, again, when you add in these contextualized embedding to the downstream tasks, like coreference resolution I mentioned before, then you can see that with using this contextualized embedding, the model perform better. So you can see the performance is increased about 4 to 5%. But the gender gap is also increased. So the discrepancy between male sentence and female, stereotypical data set and anti-stereotypical data set is also increased. Okay, so now I show you a bunch of things that the model has some bias. So how this is affect to the downstream task and affect to the human. So over the last few years, we see that people has been analyzing the gender bias in different components of an NLP model, as well as different NLP applications. So this is again just a subset of all these papers in this area. And why this is bad? I mean, in many applications, having the model to embed the gender is okay. But the problem is that if we're talking about some specific sensitive application or under certain context, that we don't want this bias in our model. So let me just recall what Fino said in the first part of talk, that there are several situations that you really don't want the model has a bias. So this is not an NLP example, but I use this to share with you the concept, like we want to have an AI that can work for everyone. Not the AI just work for majority group of people. So as you can see, this is a rare situation that I think this is a New Zealand's passport control that you need to update your photo, upload your photo, and if your photo satisfies some quality, then you can get your passport. But this guy never got his passport because the model say his eye is closed, and the model cannot identify his eye is open or not. So maybe that system can work like 99.9% fine with most of the people, but for this guy, he will have a trouble using this system. And this is something that we don't want to have when we build up an NLP system. And the other thing is that for certain sensitive application, that if you think about the job applications or like credit card application, and for this kind of a sensitive applications, then we need to be super careful because in that case, if you have a bias in your model, then you will have a allocated bias harm toward those people. Okay, so let me take the next 10 minutes to talk about is there a possibility that we can remove the bias from the model? And more specifically, I don't want to say that I want to remove or eliminate all the bias in the model. I want to think about in a different way. I want to control those bias. Yeah, because again, in many cases, you may want to have a bias in the model because that improves your performance. But the question is that is there a way that we can control what we want in the model and what we don't want to have in the model? So back to the new risk paper. So if we talk about the bias in the embedding space, then because all the word is sit in the linear space. So actually this is a nice way that you can just using some linear operator, then you can project all the word to the null space of this gender direction. So in some sense, if I don't want the gender information to be encoded for certain word, I can just project out this gender direction. Then you can somehow surgery this embedding space and do this projection, and then we can remove certain bias in this embedding model. So this is another way to do this, and you can write this bias elimination process as an optimization problem. That basically you want to do two things. So one is you want to learn this transformation matrix, that after the transformation, you can still have a same similarity between words in the embedding space. So this basically the first term I show on the left. But on the other hand, you want to project out the gender bias for certain words. So on the right-hand side, I have this term to basically minimizing the distance of those words in this gender direction. So you can write an optimization algorithm to optimize this equation, and you can get this transformation, and then this is a way to reduce the bias. And by doing this, you can actually tune a parameter lambda that you can balance these two things. So this is like some algorithm, and there are furthermore many algorithms proposed to reduce the bias once you have the embedding. But then it's also come with a question that can we just train a model in a good way such that we don't embed such a bias in the embedding at the first time when we see the data? And turns out we try to do that, and it is very difficult to do so because if you don't want the model to learn something, the model still can find some way to learn this. So at least like when you deal with your student or child, they always have a way to do something you don't want them to do. And so we try another way to do this. Like instead of asking the model to take out the gender information, we ask the model to put the gender information on certain dimension. And turns out that is more easier to do than just ask the model don't encode the gender information. So specifically, we can keep a certain dimension for gender. So in the sense that when you train the word embedding, you can initialize with all these male definitional words with 1 in this certain dimension and the female with -1. Then when you're trying to learn the embedding model, because this dimension is already captured the gender information, now the model will trying to push all this gender information to those dimensions. And then you can again design some objective to trying to promote the model to put the gender information in this dimension and out from other dimensions. So let me just show you some quick result that if you do so, and if you look at this projection on this gender direction, then you can see these male and female definitional words are on the 2 sides of this embedding space. And in the middle, you have all these words have a different portion of gender information there. And if you look at the other dimension, which should not encode the gender information, and you project that to the gender direction, then you can see that most of this gender information go away. Okay, so this sounds nice. So we try to plug in all these gender debias algorithm on the word embedding and then plugging them into the coreference resolution problem. And then you can see that we can reduce certain bias in the end application. But then comes to the question, does the gender actually remove from the word embedding, or still there are some residual there? And there is a very nice study in the NACO this year by sorry, I forgot the university, so they basically showed that even you trying to do this, they still have a lot of gender information that still sit in the embedding space. So they conduct several experiments and show that bias is still there even you apply all these debias algorithm. And here I show one figure in the paper. So in this figure, the x-axis is original gender projections of the original word embedding. So the word on the left is closer to the female, and the word on the right encode the more like male information. And the y-axis show the number of nearness. They use so the y-axis show how many like male words are in the nearness neighbor of these words. So as you can see, like some word that captains has a lot of male nearness neighbor, and some word like nanny has a less male nearness neighbor. So this is a result on the original word embedding model. And if you apply the debiased algorithm using any of the algorithm I mentioned before, then this is a result. So as you can see, not much change. You can see that this reduced the bias a little bit, but still most of the bias are there. So that's come to a question that is it even impossible? I mean, even possible to remove all these gender information from this embedding space or not? Or do we really want to do that? Because from the model's perspective, like when humans deal with the bias, we are not like hide ourselves from all these issues. We are understand there is a bias in our perception or all these things, and then trying to have some way to deal with that. So in this science paper, they also mention and also argue that awareness is better than blindness. So you should actually propagate this kind of bias to the later in your component, and then trying to resolve that in a more high level or holistic way. So this comes with which layer should we debias all these NLP models. So from my experience, you can debias a model in several different ways and on different layers. So if you do this in the embedding layer, what you hope is that the later component will take this representation as a feature, and you hope the model to use more good feature than this gender feature when you make prediction. So if you can remove the bias, even if it is not totally go away, then still there is a hope that you can see the model can be less biased, as I showed you in the co-reference resolution situation. But if you really want to get rid of a bias, then of course the bias is not only come from the embedding model, it also come from other places in this pipeline. So we also need to have some other way to debias the model in different layer. So one way you can do that is you can try to simulate the data for the other gender or for the other group of people. And if you do so and you augment the data, then there is a hope that you can reduce the bias. And Vincent later on will also talk about there are some way we can try to directly calibrate the prediction. And in that way, we can also make the model to satisfy some of our constraint, and then in that way we can also reduce the bias. Okay, so let me just spend a few more minutes to talk about this data augmentation idea. So the idea here is that whenever you have a data, let's say male data, then we can simulate a similar data set with a female. And then if we average them, then the model will see the same distribution of a male and female. In that way, we can reduce the bias. So if this is a computer vision application, that means that whenever you see the picture has a man, then you replace the man with a woman or vice versa. So for vision, this is not easy, but for language, it's actually much easier. So let me go back to this window bias data set. So we can actually simulate this thing by looking at every sentence in the training data, and then we just replace all the gender pronoun to the other gender. And of course, there are some words like name. It is very hard to do this kind of replacement. Then we can just anonymous them using some token. Okay, so if I have a sentence like this, that John went to his house, and then I first replace John to some anonymous token, and then I replace like his to her. So in that way, I can generate the sentence with the same context, but it's for the other gender. And then if we train a model on that, then the model will see the similar context for male and female. So when you do this and plugging into the co-reference resolution model, then you can see that now the model is less biased. And actually the difference is not significant, statistical significant anymore. Okay, so let me end at here and then give a phone back to Vincente. And I want to also mention that we have a ACL paper give a literature survey of a recent work on this bias in NLP model and how to mitigate those bias. So if you are interested in this topic and you can look at our paper, then there are more studies that we mentioned in the paper. Uh-huh. Right.
And they are not gendered in any way. So the gender is not marked on noun, adjective, verb, pronoun, nothing. Mm-hmm. Yet there can be very strong biases because there are semantic genders everywhere. Right, so how do you debias the data or augment the data there?
That's a very good question. I don't have a good answer here. Yeah, that could be a good study to do so. Yeah, I should mention that there are also some paper trying to do the thing I mentioned using the morphology, and then you can deal with other language than English. Yeah. Yeah.
Hi, everyone. So I just came from Seoul in South Korea, attending the International Conference on Computer Vision, which is, like I would say, the main community where I move. But I also do a lot of work with language, and I work with people like Kai Wei on debiasing word embeddings. Prominently, we have also been debiasing and applying some of these ideas to vision problems and visual recognition models. Seems like my Mac is not very friendly to this setup. Okay, we're back. And we're not. Okay. So, nobody moves. If anybody has any questions for Kaiwei, please feel free to do so at this moment. Let's try to.
Yeah, if anyone has a question, we can try to answer. Oh, he's asking that in my slide I have some orange and then blue dot, right? And yeah, I try to use that to represent male and female. Yeah, and the bigger circle or smaller circle represent a different, population of those people in the data set. Yeah.
Just stay in the side. Don't go to the right.
All right. We're going to do this. All right, so I'm going to talk to you in a little bit more level and detail on some algorithms that people have come up with for learning fair representations. So I'm going to talk about issues that people have identified in various systems, including NLP and computer vision, and things in between. Metrics, findings, and solutions that people have proposed. So a lot of work is being done in computer vision on grounding language in various ways, or generating language from simply just image classification, assigning a set of words, giving an image, to producing a natural language description, to producing some more complex linguistic structure. And we're going to look at these three types of problems. Here is the simplest one, which is classifying an image. And so here we have a set of images, and the labels could be as simple as, is there a kitchen or not a kitchen, which is a binary classifier. And we could have a protected variable in this case, which is gender. This is a very common setup. So the idea is that if you build a classifier for this type of problem, you want the following to be true for any pair of gender types. You want to be equally probable that there is a kitchen, given that there is let's say, a man in the picture or a woman in the picture. And the same is true for the case where there is no kitchen, right? So you would like that to be true in these problems. So one possible way of solving it is, this paper from 2013, Learning Fair Representations, University of Toronto, Richard Semmel, Little Wu, Kevin Swarsky, Tomia Pitasi, and Cynthia Dork. And the approach, I'm going to explain it right now. It's very generic. They did not use any images or text in their experiments. What they used was mostly a categorical data set. But I think it's general enough. So the idea is that you have some set of inputs. X, in this case, could be the images with kitchen, no kitchen, and a set of labels, Y. These are, kitchen, no kitchen, right? These are your labels. And the idea is, traditionally, you learn a mapping function from X to Y. Instead, in this paper, they advocate for having an intermediate representation. I'm going to call it Z. And so the idea is that you're not going to map directly from X to Y, but you're going to map from Z to Y. And here, Z are going to be these coefficients that define the mapping from X into a set of basis vectors VI. So here, X with the hat is going to be an approximation for a given image, X, for instance. Could be anything. Now, that by itself doesn't take us anywhere. This is not more fair than it was before, but it's a way of mapping from X to Y through an intermediate space Z. Now, in this paper, they subdivide the images X into two groups. So these two groups could be more groups. I assume you could extend this, but they try with two groups. So these two groups could be images of women cooking and images of men cooking. So these two groups are defined based on your protected variable. And so what you want is that these representations Z, these coefficients that define how to reconstruct a given input X, should be distributed more or less the same for both of these groups, X plus and X minus. So they have a proposal where they use this loss function. So the loss function might look very complex, but essentially is trying to achieve three things. The first component is just a cross-entropy loss, which is very common for classification. So you want your classification still to be good, so you should optimize that, absolutely. The second term is a reconstruction loss. So your reconstructions need to be good. So your projected X with the hat should be similar to the original X inputs. So that's the other objective. And then they have this third objective right there. So that objective is that we want those intermediate representations Z to be indistinguishable across the values of the protected variable. So this could be accomplished in various ways. So here what they're trying to do is they're trying to make sure that the mean values of those Z computed across each distribution. So here you have the mean of the Z's for the males, and here you have the mean of the Z's for the female. You want these to be as close as possible, as similar as possible. So, but we know that the fact that you have two distributions that have, or two groups or populations that have the same mean, it doesn't mean they are equally distributed, right? You could have two groups of things. The mean value is the same, but they are completely different in many other ways. So actually this doesn't quite guarantee that your values in Z space will be indistinguishable, but it encourages that. So it manages to reduce the differences between the groups you care about to some extent. And there have been proposals to match maybe here higher order statistics in this intermediate space. So this is why the intermediate space perhaps useful, because you can manipulate the intermediate space in these various ways so that groups are indistinguishable there, right? You can't change the inputs, but you can change this as an intermediate representation. So that's the idea. That's the approach number one. Approach number two that people have been aiming for this problem is the adversarial feature learning approach. And so in the adversarial feature learning, you have a model, it maps directly from X to Y, and this model computes at the end some features, also Z. And then those features Z from this model go into a classifier. So the idea in the adversarial approach is to have two losses, two objectives. So the first objective is your classification objective. You want to classify kitchen or no kitchen, so that's your task. And the second is an adversarial loss. And this is trying to make this second classifier not be able to predict gender from those features that you're feeding to the other classifier. And the idea is to train these two things together, like the same way you would train a generative adversarial network, a GAN model. So you have these two losses competing with each other. So one is trying to predict kitchen, the other is trying to not be able to predict gender, right? So there are several papers that have proposed these. This is one paper where they specifically had an experiment with images. They did not have this specific experiment that I'm showing you here, but they have this experiment. So faces. So they had these images of faces, and the objective was actually to identify the person in the picture. However, these images were captured in such a way that you had the illumination coming from below the face, the side of the face, top of the face. So some of the algorithms might be more tempted to match things that have the same illumination, the things that have the same person. So actually in this paper, they did not approach the problem from a fairness perspective, but rather from a feature invariance perspective. But a lot of the methods that people have developed for feature invariant learning actually are very related to fairness and robustness. And they also had this very nice figure where you can see in this corrected feature space that images don't cluster based on their illumination as nicely as if you use the original space. So this is the other approach for this kind of problem. Case study number 2, and this is a task that has a little bit more of a NLP grounding. So here is visual semantic role labeling, and the task is given an image. You want to predict a frame with its roles and values. So in this case, we want to identify people carrying, for instance, and not just whether there is a person carrying, but also who's doing the carrying, the item, the part of the body that is doing the carrying. And all of these values will change the appearance of the images quite a bit, quite noticeable. And one thing we found, and this is work I did with my students and also my collaborators, we saw that there are a lot of images of people carrying backpacks, but there is not a lot of images of people carrying tables. So this is another form of data bias related to reporting bias too. So these things happen in vision as well. However, there are a lot of images of tables in the data set. So how do we leverage that? So we propose a model where we had a set of object embeddings that were shared across many categories of actions. So even if you haven't seen table many times in certain category of action, but you have seen it in others, you could still leverage the appearance of table from these other categories by having these global noun representations. So we modeled this as a CRF, where a convolutional neural network was computing the potentials of this CRF in a compositional manner. So we had this demo where you could run some images and online, and you can get some predictions. For instance, here it says there's a person falling from a horse. But then as we started to try these more and more, we started to see that some rather problematic patterns started to emerge. So here you have this picture, and the prediction is there is a woman rinsing her hair on the sink. And the second prediction, there is a man installing the faucet. And then we try this other image, and the system says there is a woman dusting the faucet or vacuuming the floor. So these were clearly problematic stereotypes. And maybe we thought this is just what the data set looked like, and we don't have much hope for fixing it. So we looked at the data set. So in the data set, we looked at images of people cooking. And indeed, there was more women cooking, for instance. So the model would learn that pattern to produce that pattern more often. So, but we took the model and we run it on some test images, and we tried to see to what extent this is replicating those patterns. It turns out that in the test data, is amplifying this ratio. So the problem becomes not just words, not just replicating it, but really amplifying. So we call this bias amplification. And we propose some way of alleviating this problem, really not fixing. So the way we did was to have this corpus level inference method where we have two objectives. So the first objective is the usual objective, just a classification objective. We still want to be good at classifying these actions. And then we have another objective, which is to match the ratio in the training set to that one in the test set. And again, this is collective inference, so we can't run this at a single image. Using this method, we managed to remove the bias a bit, but still it doesn't match the distribution in the training data. We could match the distribution of the training data actually if we optimize and give more weight to the second objective. But that would hurt the ability of the model to classify correctly whether there is a kitchen or not, for instance. So this is the result we got by maintaining the accuracy of classifying actions as much as possible. So we can find a classifier that has a slightly less skewed gender ratio, and it works just the same. There's no compromise. But we are compromising still on. This is not quite matching this, right? We also have a more recent work where we study more general bias amplification, even for models that are not predicting a structure. They're not predicting the gender. Like, you might be interested in classifying just images into kitchen or kitchen, but you don't mind in predicting the gender. So we also came up with a different measure of bias in this case, because now we cannot just look at the test data and look at the predictions and see what is the distribution of that the model is predicting for men cooking, or, because it's not predicting men or women anymore. So there is this paper in 2018, and it's actually an EMNLP paper by Elazar and Goldberg. And here the idea was to classify tweets. They had a sentiment analysis task. And the idea was, well, I'm going to train a sentiment classifier. And this sentiment classifier is going to be a neural network, a recurrent neural network, I believe. So they took the features that the recurring neural network learned for each of these tweets. And then they tried to predict the gender of the person writing this text, for instance, just based on the features, not on the original text. How much did the model preserve gender information in the features that it learned for a separate task, for a task that is potentially unrelated to the problem of sentiment analysis? So they found that they could predict the gender actually pretty well, or age, from the features. And so they call these gender leakage or just leakage. So we took this idea to the vision domain, where the objective is to tag an image with a set of words. So here we have an input image, and these are the annotations of that image. These are the true labels for that image in the data set. So we did something different here. So we took the labels, and these labels don't include person. They don't include men or women or anything like that. They just include objects. And so we train a classifier on top of these annotations to see if we could predict, based on the objects in the scene, whether there is a man or a woman in the picture. And we could do it pretty well, actually. So we call these gender leakage coming from the data set or the task. So the task itself is biased. We also train a model on this data set. And then we computed some predictions for a set of images. And then we ran the following experiment. So now we're going to try to predict the gender of the person in the picture by feeding to this classifier the output label predictions of the model. And this model that was trained on this data set for predicting objects was not that great, right? So it produced an accurate level of 58%. The ground truth labels are, of course, 100% correct. Or at least we assume so. I mean, there might be some label annotations. I'm ignoring that. But you get 58% here. However, the gender classifier on top of these outputs can predict the gender at a higher accuracy than on the ground truth labels. We call this gender leakage that is coming from model predictions. And for short, we actually, in the paper, we just call this dataset leakage and model leakage. But essentially this is the capacity that you have to predict your protected variable from the outputs of your task. Both the ideal outputs, the ground truth labels, and the outputs that you're getting actually from a model trained on these labels. And of course, we use separate splits and so on. We use the same set of images. So actually, we thought, what if we had a model that could predict a 58% accuracy, but for the things that it makes incorrect predictions, it would be entirely due to random noise. So we did the following. We extended the notion of dataset leakage to dataset leakage at accuracy X. So this means we added some random perturbations on the ground truth data until we obtained annotations that were 58% accuracy, which is the same accuracy we're getting with our model. So the difference between these two set of predictions is that the first set, the errors, whenever there is an incorrect label, it's always because we randomly flip it with something else. In the model below, whenever we have an error, it's due to some systematic pattern that the model learned. And so here we still found that the model leakage at the same level of accuracy as the dataset leakage is still higher. So our definition of bias amplification became just the difference between the model leakage at accuracy K minus the dataset leakage at accuracy K. So we tried this on a dataset that had 73% men and 27% women, which is not uncommon in some of these vision datasets. And we measured the model leakage and the dataset leakage at 58 and 58. So we could find that the model, you're able to predict from the outputs of this model the gender at this rate of accuracy, almost 70%. But if you had a model that whenever it made wrong predictions, it would be due to some noise, you would be able to predict at this rate for this data. Now, we try to balance the data set because we thought the data set is unbalanced, but once we balance, maybe this will go down. And it went down. So here is more balanced. So the ability to predict the gender is less now because it's more balanced. But the difference between the leakage in the model and the data set is kind of similar. We also try to completely balance the data set. By the way, balancing the data set is not easy because here, this is not a binary classification task. It's not like kitchen, no kitchen, where we could like say, okay, we're going to have half the images of kitchen with men and the other half with women, half of the images of no kitchen with men and the other with women. You know, we could have that there, but this is not binary classification. This is multi-label classification. And the objects co-occur a lot with other objects. So it's hard to balance across all these objects because you might have an object that has an umbrella and a person wearing a tie. And then if you try to balance the person wearing tie thing, then you're unbalancing maybe with respect to umbrella. So it's hard. So we actually had to run some sort of optimization itself to get this balanced data set. But we did. It's pretty much balanced. So the data set leakage is almost 50%. But we still have model leakage. We're still able to predict the gender from the predictions of the model. And this is, we think, we're almost certain, that we cannot balance with respect to other things that are not annotated in the data. For instance, it could be the case that all the men in this data set are wearing dark clothes or something like that. And we can't balance with respect to that because that's not a variable that we have annotated in the data set. So we tried to solve this problem too. So we were not just, we tried to address the problem, I would say. So we tried also adversarial feature learning, which was proposed again in this NeurIPS 2017 paper, which was applied to faces. And we tried to apply it here, right? So we're going to try to predict our classification, and at the same time, we're going to try to not be able to predict the gender from the features. But actually here we had a very deep neural network with 50 layers. So another thing we tried in this paper was to debias some of the intermediate representations that the model was learning. And we found that actually trying to remove the gender from the very last layer is not the most effective thing. So we actually ran an ablation study and we tried to debias the neural network at several entry points in its layers. We found that the best was to try to remove the gender from some layer in the middle, not too close to the inputs, not too close to the outputs. A little bit closer to the outputs, I would say. But we don't know what the model is removing, right? So these intermediate layers in deep neural networks are obscure and not interpretable. So what is the model doing? So we also came up with this other model, which removes the bias too. Doesn't work so well as the previous one. I did not do anything. Okay, we're back. So, all right. So the idea here was that we use this sort of autoencoder thing at the beginning of the neural network so that we can remove biases in input image space. Because input image space is something we can visualize and understand. So here are some of the results, so we can see what the model was trying to remove from the picture. So the model tried to remove faces, even though we didn't have annotations for faces. We didn't provide those. It detected even faces that were not frontal faces, which is kind of remarkable because a few years ago, detecting profile faces was itself a challenge in computer vision, even with full supervision and lots of annotations. Here, the only supervision we have is like, we don't want to detect gender in these images. It removes the skin also. We also saw some instances where it removes some objects that might be very tied with one or another gender, like a pink umbrella, apparently. And even when we had multiple people, this kind of worked. So here are some of the quantitative results we had. So in the x-axis, you can see the bias amplification. And in the y-axis, you can see the accuracy of the model in predicting these actions, for instance, or the objects. So you can see that removing the gender at the convolutional layer number 5, not really number 5, is the fifth group in a ResNet network, so this is convolutional layer number 40 something. It was the most effective, so we can retain almost all the accuracy of the original model, and the bias amplification becomes very close to 4. But we tried other things. So you can see in this figure, we tried to just run a face detector and remove all the pixels of the faces, because we thought that should prevent the model from that should prevent any prediction of gender. Turns out no. Like you can see that the leakage is still quite high for this model. And the accuracy stays a little lower even than the best model we had, which was debiased. We even tried to remove the whole person. Just remove any pixel of the person, put a box on top. So that removed the bias almost to our best model, so between 4 and 6, but the accuracy was also much lower. Because removing the whole person also will remove some of the objects you care about, so we can't just do that. So this is another work we did. So finally, the third type of problem in vision and language, and this is a very popular one, is image captioning. So taking an image, you feed it through a neural network, and then you feed that to an RNN, which produces a sequence of words. Maybe now you're using a transformer model for these. So the idea is that every time step, you have a loss like this, a cross-entropy loss that predicts the words, the next word based on the previous word, and maybe the image features. So in this paper, ECCV 2018, by a group at Berkeley, they found things like this, like sometimes the model would predict a woman cooking a meal, but it's really a man. But it does so because the background, maybe. Or, a man wearing a black hat, is snowboarding, but this is actually a woman. Or seems like it's a woman, at least, if you look at it closely. And so the paper was called Women Also Snowboard, which was building on this idea. So they proposed the following approach for debiasing. And again, this is something that could apply to many other problems. So in addition to trying to predict a good word, like this is caption correctness, with a cross-entropy loss, they have an appearance confusion loss. So they augmented the data by occluding the person. So here, there was a person. They just put dark pixels instead. And so the idea is when you occlude the person, whenever there is a location where you're supposed to predict a gender word, like man, woman, girl, boy, all of these words, there should be equal probability of predicting either of those because you can't really see the person. So they enforce this. So they have this confusion loss. So for these images where they occlude the person, they encourage the model to be uncertain about whether to predict a man or a woman word in that location. This is the first thing they did. Second thing they did is to add a confidence loss. So for images where they didn't remove the person, right, if they had the word man in the caption, they had this confidence loss which tried to discourage things like this from happening, like the prediction of the word being man with 0.95, or at the same time the next second guess woman with 0.92, something like that. That shouldn't happen. This should be treated as mutually exclusive. So this is what they applied, the criteria they applied here. So they have these confidence laws where, again, they group the words into male words and female words. So if there is a male word there, you want to downweight any of the female words. Or if you have a female word there, you want to downweight the male words. So you want them to be exclusive. You encourage that through these other laws. So they combine these three losses, and they produce this combined model, which they call equalizer. So these are the three types of tasks in vision and language. One is classification. The other one is visual semantic role labeling. And finally, image captioning. So if you have any questions, please let me know. I want to thank my students, collaborators. And sorry I'm not in the best shape possible to give this talk. I'm a little sick if you haven't noticed. But I'm going to take questions. So please go ahead. Thanks. Thank you. If you don't have questions, then Vinod is going to give the closing remarks and take more questions for any of the people who intervened today.
Can you load my...
Where are they?
It's in that link if you... I had sent it. Oh, it's or we could...
You want to plug the other one?
Yeah, that's fine.
Okay. There you go.
I will have to refresh it. You did, or? It's a weird place to connect. Why not? I may not need it. Okay. Did you refresh? I'll do it once more. Yeah, mirroring is done. No, it's extent now. Duplicate, right? Hi. Okay. So, I mean, I have like a very few slides to close the tutorial, and then we can have more questions if you have any that you haven't asked in the previous sections. This wouldn't take a long time, so get ready with your questions. So, like, just to conclude, one of the main kind of themes that we were going for in this tutorial is that data and the biases that exist in data really, really matters. So find ways to sort of like always try to look into your data in like many different slices and dices. And as you were, as Vicente was talking about, like, you know, at one point they had like look into the data to see actually what is happening to sort of like find ways to rectify the biases. So always look into data sets in much more depth than like we usually do. And you could use like all sorts of different like tools that are out there. And like this is like a kind of like a tool that a group at Google called PAIR, People in AI Research. They have put out in this, they have like a suite of tools that allows you to like look into different modalities of data and like different kind of this kind of aggregations and look at patterns in the data. And this is not the only tool that's out there. There's many others. So definitely, you know, one thing that we could do is to look more deeper into our data sets, but also when we publish data sets, like rather than giving just the number of text sentences in the data or like some very aggregate statistics, try to give like more kind of like context of where the data came from, who were the annotators, and what's the kind of like context, like what's the kind of geographic representation there, and all sorts of different dimensions of the data that we don't usually look for, but like first try to sort of like collect that kind of like information, but also when you release the data set, the users of the data set could know where this data came from so that they can be mindful about like what potential biases can creep into the data sets. And so this is like, there are many different models that is proposed to do this, or rather frameworks. So one is work by my colleague Timney Jebru and rest of her team when she was at Microsoft on like sort of this idea of like data sheet. There's also this other kind of frameworks that has been proposed. The another thing that I would say is about releasing our models responsibly. And just like when we release the data sets, like we communicate like as much information that we can to its users, we could be more transparent about our models. And the idea of transparency is not a new thing. Like, you know, the electronic components, like, you know, for decades, they have this like standards of like how they communicate like different operating characteristics of like an electronics component. If you want to go buy a component, you have this something called like a data sheet where it gives like very detailed descriptions of like what its what its performance is at like in different temperatures and like different other operating characteristics, because they know that if such safety mechanisms are not put in place, and if the transistor or the capacitor is used in like a temperature that is not safe to be used, it could blow up. And the same thing we could think of like machine learning models could have like a framework to communicate that, this is a model for like predicting toxicity, or this is a model for doing like resume matching, but it should be used in these kind of like context, or like what's the performance, rather than communicating just like 90% accuracy, like just communicating that, yeah, if you use it in this kind of data sets, like it's 95%, in this kind of data sets, it's like 65%, and that information being transparent and having like a framework to communicate those information at that level of disaggregated evaluation to the users would be also beneficial. And so for this, there was a paper that earlier this year was published at FASTAR, called Model Cards for Model Reporting. This came out of our team. So basically here the idea is that such a report could actually focus on transparency of the model performance to encourage responsible AI adoption and application. It can also be like attached to the model so that it can be discoverable and usable artifact, so that like a diverse set of users and public stakeholders have a better or like richer understanding of the models that they're using. It can also keep the model developer accountable to release high quality and fair models across different dimensions. And again, this is not like the only framework that we could think of, but like I think it's a really good thing for our community to sort of come up with like a framework, a unified framework where we can communicate this kind of information. This is just like some example information that could get into a model card, and Google has already released model cards for like some of its tools out there, and so this is like from taken from like the actual paper that was published, but not the actual model card that was released like months later. So this is like, it could talk about like the intended use of this model, different factors to consider, the metrics that were used for evaluating them, the training data that was used. It could also give information about the ethical considerations of using this kind of like a model. You can think about like many different ML models that could have like ethical questions, and this could be a way to communicate that. And also disaggregated evaluation. So this is like the disaggregated evaluation of like the toxicity model that I was talking about. And in fact, I think earlier this year, the Jigsaw's Perspective API team did release a model card with all these kind of components, like as a kind of like a soft launch. And soon there will be like a hard launch where like Google would be like releasing more model cards for like other tools as well. So in summary, always be mindful of various sorts of biases that exist in our data and that might be captured and propagated in our models. Explore debiasing techniques, and many of the debiasing techniques that Vicente and Kaiwei talked about. But when we use them, be cautious. Like as Vicente was pointing out, like there's like limits. Like once you get to a particular point, we don't know how to like go beyond that point to actually debias them, because there are like patterns in data that we don't have necessarily annotations for. So be cautious when you use that, but also critically think about what we are debiasing against and what such interventions might be adding, or like sort of like are we adding other biases in that process? And I think Kaiwei talked about some such scenarios, but also critically question, when we say debiasing along gender, most of the work that we talked about think about gender in a binary way. Is that the best that we can do, or should we? How do we think about like a non-binary gender? Also thinking about race. I mean, what does it mean to actually put people in a racial category? And like, those are questions that we need like to engage with like social scientists and to sort of like come up with ways to incorporate that in the way that we address that in our machine learning fairness work. And also contextualize it with the kind of socio-technical systems that we are working on, rather than in abstract. Like, always think about the biases that matter for the particular problem that you're trying to ensure fairness for, and think about like who are the people what are the potential fairness or unfairness dimensions that could exist there, and then go after that, rather than like there's no kind of like I personally don't believe that there's a global fix for fairness, but rather all these techniques would be useful, but like it needs to be done within the socio-technical context within which these models operate and are deployed. And also consider this as an iterative process, rather than like we fix the fairness by doing some algorithmic or technical intervention and like expect that it would fix it, but always be mindful about the fact that there would still be people that we haven't thought about, people who we haven't seen or heard about, who might be hurt or impacted negatively by our model. So think of it as like an iterative process when we intervene on like these fairness issues. And also, as I said in the last few slides, be transparent about our model and its performance in different settings so that the users can make more informed judgments on how they want to use it. On a closing note, I would, just to sum up what I just was talking about in the last slide, fairness and justice are properties of social and legal systems. To treat them as terms that have meaningful interpretation or application to technology separate from the social context in which these models are deployed can be an abstraction error, and that's an error that a lot of machine learning fairness researchers, including my own work, like we have actually probably be committing that error, but like being mindful about it and like doing research in a socially contextualized way would be super important as we look forward. And from here, I think that was like 10 minutes maybe. Any questions on this section or like any other sections, you both can come up to the stage and we can figure out like how to go back to the slides if we need to.
Thank you for a really excellent session of, to me, illuminating perspectives on bias and fairness. I have a question, mostly on the closing remarks that I think anyone can respond, but specifically with involving social scientists into research on bias and fairness. I can give you a little background. I'm in an interdisciplinary lab with computer scientists who are just now trying to get into research on bias. And I have social scientists in the lab itself who read these papers about bias and fairness and said, what do they mean they're researching bias? And I imagine there are a lot of psychologists, sociologists, et cetera, who know a lot and can offer a lot to this research community, but I don't see clear inroads to do that. So I'm asking what you think are some practical ways that social scientists in general that don't have current contact with this community and social scientists that are trying to work on machine learning, NLP type projects, what are some ways that they can get involved?
Do any of you want to respond? Yeah, it's a very excellent question, and I think it's a problem that I face myself, and like many of the research that I've been doing in interdisciplinary collaborations don't come in very easy. To just take an example, like I co-organize a workshop on abusive language detection, and so as part of that, and that's like an inherently interdisciplinary inquiry, like in how to address that. And so we try our best to bring together social scientists and computer scientists into the room for that one-day workshop. And like for the last couple of years, like we have a really great workshop, but I know that, or I feel that just to expect that, like putting them into one room and like expecting that magic would happen is, I feel like that it still needs a lot more to be done to actually get like really meaningful collaborations out of it, to actually impact each other's work rather than just like seeing there and like, and I think that's really, like the challenges that you were talking about are the challenges that I also think exist in like, so there's a lot of like translation issues, like in terms of like what does these different communities like their own different ways of approaching these problems, and so in terms of so I don't have like solid ways to suggest like what would work in that to address that problem, but I know that many people in the field, in the fairness research in general, has been thinking about this issue as well. There is a workshop at the FATSTAR next year in Barcelona in January, where they have actually a session exactly on that. And I think their session it's not a workshop, it's like a craft call. It's like a kind of like a open-ended kind of structure where they are going to select like a bunch of papers and make the computer scientists read a social science paper and the social scientists read a computer science paper on stage and sort of like discuss like their interpretations rather than like reading it in their own room and be like breaking their head on their table. It's doing that on stage so that like the gaps like that you have identified could be discussed and like out in the open where the computer science and social scientists on the in the room. I thought that was like a really excellent proposal, and I'm looking forward for that session. So I think it's a big problem that I don't know like clear answers to actually address. Thanks for the question.
I just want to add a few words about my personal experience. That so in several of our collaboration, we also talk to social scientists and get comment from them. And most specifically, I have a few recent projects with people from public health that they have all this social science background. So I think one thing is that as a computer science, I'm not a social scientist, so I cannot speak for them. But I mean, from my perspective as a computer science, especially on NLP, I would say we need to know our limits, right? So most of the time, I'm not trying to say this is a definition, this is how we should do it, how we should get the model done in that way. But the way I see all the work I did is more like this is a way we can control the model. So it's back to the NLP question that you want to control the model in the way you want. So the social scientists can give me the criteria or all these things they think they are the right way to solve the problem, and my job is more like trying to make this happen. Yeah. So so a lot of conversation is like that. They identify what they want, and I tell them, okay, this is not going to be able to do it, or this is something I need to spend maybe a few months or more few years to do research and trying to approach that. Yeah, so with this kind of a conversation, people know what we are looking for, what we can do, then that would be more easier to collaborate. Yeah, that's my just personal experience.
Any other questions?
Yeah, I don't think I have much to add. I mean, I also run a group at the University of Virginia. University of Virginia has a lot of people in the humanities and social scientists, and so we have a weekly group, and collaboration is hard with other communities in general. I mean, computer science, we move in conferences, and social scientists move in the journals, and funding schemes, at least in the US, are through completely different channels. So I think the only thing I've been successful is to just put people in a place and have a conversation and read across fields. So we've got feedback with, like, we didn't get it right the first time sometimes, but we get feedback and we try to improve. That's what I can say. Does anybody have any question? Does that answer your question also? Okay, I hope it was not too despairing. Anybody else?
So thank you three for the nice tutorial. For Vinod, in the first section, you mentioned, I think there was a company that was dealing with toxicity, and there was this example of certain terms that were not toxic that were being misclassified as toxic. And you said that they had some solution to that. They were able to mitigate the problem. I don't know to what extent you're able to shed light on how they did that, but I'm curious if you can.
Sure, thank you. Thanks for the question. They published that paper, I forget which conference, maybe AIES, which is AI Ethics and Society conference last year, I believe. I think they approached it with like a counterfactual talk on fairness approach, I believe. So they basically use these like different groups of identity terms, and they swap the identity terms between, like, say, straight versus gay, or like, or like different religious groups and stuff like that. And they brought that into the objective function. in the prediction framework. So I mean, it's basically perturbing the sentences during training time, perturbing the sentences along that, like in that particular token, and to sort of like mitigate that. But that worked in that situation because it was like a finite set of identity terms that they were going after, and they were mitigating for that. And the caveat that I place there is that the bias towards like LGBTQ terms, for example, does not necessarily only happen on the terms gay, lesbian, like just that words. The LGBTQ person's identity is revealed through so many other factors of the text that they use. Like there probably is patterns of text, just like gender. There's like different topics that we might be talking about. There might be different like linguistic patterns that we might be using. I mean, I don't have empirical evidence for it, but like there could be. And those things actually act as proxies for the identity term. So it's a false sort of like assurance that actually solve the LGBTQ bias, if there exists one. It's just that it was whatever it was revealed through that inquiry or like that probing using the identity terms, they were able to mitigate it. But there may be other ways that same groups are being disadvantaged, which we don't know about yet. Thank you.
Yeah, thanks a lot for the talk. It was super interesting. My question is about, there was this one paper about like debiasing word embeddings, particularly with respect to gender. There was like this chart with the y-axis being like sexist at the top, and I think definitional was the word you were using for the bottom side of the y-axis. If I understood that paper correctly, the method for determining like that y-axis was essentially just like a manual classification of like these words are definitional and these ones are not. I wonder if anyone has any thoughts about what's happening in that process, and like maybe the ethical questions that are implied by this kind of manual classification.
It's this one, right?
Yeah, it's this one, right?
Yeah, this one.
Yeah,
exactly.
So that is the paper that we have at the NeurIX 2016. So what I didn't mention, but we did at that paper is that we also try to just train a linear classifier to trying to see if the model can identify the word with a definitional gender or word just have some gender components. And you just go through this standard machine learning pipeline, and you can get like 95% kind of accuracy on identify that, which is not perfect because there are a lot of the error are making on all these important words. So you have like 5% of a word that misclassified and might not work well there. But kind of showing that these two type of words are slightly different from model's perspective. So then we use that model to classify all the words. Yeah, but I mean, again, I definitely think there are better way to do this. Yeah.
But the original training data that you were using to train that classifier is just kind of manually labeled, right?
Yes. These are from the Amazon Turker.
Gotcha.
Yeah.
Okay.
Thanks for the very interesting talks. So my question is on I think one of the issues with AI ethics right now is like a lot of people can build systems like machine learning system and deploy it to applications. Like we have NLP systems in application for hiring, for criminal justice, for like medical record processing. I'm just curious from the research perspective or from the researcher's perspective, like there are so many real world systems that are in deployment right now that have potential a lot of issues. Like, what do you think are kind of the best avenues that we as a community can be helpful in terms of kind of effecting change in those systems that are already potentially propagating bias into kind of a large community?
Yeah, I can just add a simple thing. So I think as a community, we need to think about solution in different levels. So that's also part of the thing I was trying to say, that there are something like, for example, word embedding. We know it's almost impossible to debias, but people just plug in and go. So if you fix something there, then that might have a bigger impact. But the problem is still there, right? And then there is a different layer of research that we can do and trying to solve this problem. Yeah, and I guess Vino will also mention some other thing like transparency or other thing can help there. Yeah.
Yes, I think there should be a better vetting system for deploying some of these things, especially when they affect people so severely in applications like predicting somebody's going to commit a crime or something like that, or credit scoring that could be discriminatory. I think the onus is on the person or the entity producing this technology to prove that this is compliant with some basic, at least, tests. I mean, they have to convince people that this will not harm them. And the way to implement that, I mean, it involves the technology, certainly, the people producing the technology, but also law. So I was at this recently talk by a legal scholar on algorithmic fairness. And it's still a very complex issue. There is not the proper framework for regulation on these issues. So based on some of the prior, and depends on jurisdictions, right? So at least in the United States, I mean, to prove that some of these systems are not legal in a way, would require to prove that the algorithm creators intentionally injected these biases, and that is something that is hard to prove, for instance. So I think there are legal, sociological, and technological challenges to overcome. Absolutely.
Yeah, I agree with both of them. But I also want to add that, like, so some of these challenges are like, for example, if like it's in a big company where like you have like thousands of people working, you could have like a group looking into like these sort of like fairness issues. But like if it's a startup who has a product, they may not have the resources all the time to sort of like sit down and like sort of like look at these issues, but they may be also affecting like people's lives like in significant ways. Like it may not have like as much reach, but like it may be, there are startups working in all sorts of different like verticals and like affecting people's lives and access to resources and access to medicines. And so it's a superbly important problem to actually, or like challenge to work on, to find the, like ways that are successful ways to sort of like what, as a research community, what we can do is, as they both suggested, like sort of like engaging with like I think policy folks to actually see. I think there's a lot of awakening in the legal system and like in the policy folks like about like these issues and like coming up with laws that actually deal with these issues. But it's also important that as technologists, like we engage with them to actually make sure that kind of takes into account the challenges that technologists have, like in terms of like doing things at scale. So engaging with like that kind of in that kind of conversations to make sure that like the policies are put in like in the right kind of like framing. But yeah, I think that's it's a hard thing. Like there are a lot of like tools that are out there which are like doing, it's only, we are hearing about things only when things go wrong, and like there's like a PR nightmare or like some sort of like but there's no kind of proactive ways of like preventing things before making that change. And one more thing that I would add is like it's a long-term thing, as like I think incorporating AI ethics into our curriculum in the education system. When we teach AI and machine learning in colleges and schools and universities, thinking of ML fairness as like, or machine learning fairness or AI ethics as like a elective or like something like your focus area. It should not be a focus area. It should be something that's fundamental in like teaching AI in artificial intelligence, so that like it's the example that I always use is like whenever a machine learning researcher uses like the training set versus test set, like the training set and test set should not mix is something that we have so inherently like learned that we would never do, like a responsible researcher would never do. So I mean the ethical considerations of like the models that we are building should be kind of like something that's fundamental, that like brings in like that kind of considerations should be made fundamental, and that has to change. That can be changed through like education and integrating like these concerns and these perspectives into the curriculum itself from the get-go would be super helpful. But that wouldn't address the problem that you raised, but like in the long term it could. I think there's like more questions now. It's what time is it? 12:30. It's 12:30. Anybody who wants to go can go, but we are happy to take more questions. Is it okay?
Hi, thanks for the tutorial. I had a couple of questions specifically about debiasing on the modeling side and control, which I think you talked about. Particularly, I guess my understanding of this, especially in the Bullock-Biasi work also, is that there is kind of this fine line between removing gender associations and maintaining those that are valuable, and this is kind of done in a very discrete way in this work by having these two word sets that with bias and then words associations that we do want to preserve. So I guess my question is, this line seems very like social and cultural, as you mentioned, and how in a specific application do you kind of determine how much of a certain like protected attribute do you need to retain or do you want to erase?
This is a very good question. So I would say this work is more like the first few were trying to think about this question. So there are several things that when I look back, and I would definitely want to change. So the thing you mentioned is one thing I might consider to change, that don't have just very specific. This is something I want to keep. This is something I don't want, but have some other methodology to somehow balance those things. So I think in terms of the question you are asking, that for which application you want to keep this or that, I think this definitely application oriented, right? It's back to what Vincent and Fino also mentioned, that for different applications you may have some fairness concern you want to consider, and then that can give you some evaluation matrix. Then those matrix as an end task will tell you that do you want to keep these or those things during like different layer of the model. And again, a lot of things I mentioned here, I don't want to say this is a right thing to do this or that. It's more that this is a bunch of Swiss keys that you can use to do this and do that, and then how to use those tools should be decided by someone who has a better understanding of all these human culture, those kind of things.
I will add to that question. That for me, I mean, like sometimes people focus too much on obtaining good accuracy on some data set that is fixed. And so under that point of view, you're making some trade-offs, but these might not be real trade-offs in the real world. Like you might have a system that is deployed in the real world and they will see like all types, all kind of people cooking. For instance, in your data set, you might get away with a little better accuracy because just the way it's distributed there. But in the real world, I think reducing this bias not only reduces a social issue in my mind, it also makes the models more robust, just period, better, more generalized to more situations. I think from that perspective, I'm also interested. And it might be a better way to sell this problem, because in a real deployment application you can't foresee, you can't control the distribution there.
So first of all, thanks for this very interesting tutorial. I learned a lot. And so all the work that you have presented here has one common thing, that you start with one hypothesis that what might be biased. And I have read in some literature they call it the sensitive variable, like it could be gender, it could be race, whatever. I'm just wondering if it even makes sense to ask this question, that whether machine can itself analyze the data and come up with potential dimensions in which the data might be biased. Has there been work in this direction?
Thanks for that question, and I wanted to add a few slides on that, and I think in one of my closing slides I kind of talked about it, that the dimensions, like I think the gender and race is like most of the machine learning fairness work focuses on that, and I personally have a feeling that like it's a very US-centric or like Western-centric perspective of fairness, and in different geographies and different cultures, like the axis of discrimination would be different. Like in India, it would be caste or religion. In Indonesia, I don't know what it would be. In Africa, it would be different. So it's like those are not even represented in the way we are framing our problems and going after them. So that's a point well taken, and that's like something that's lacking in the community in general, I feel. But also I should point out that there's like some work that actually tries to get the machine or like to look at unsupervised ways of like detecting biases. So one work is from Yulia Setkov's team at CMU. They have this like topical bias. So they do an unsupervised topic modeling and then looking at like biases towards topics to see, and then like those topics may have like gender or some other sort of like correlations. So that's one work that I know of. There was also work by Maria Ortega, I forget the last name, it's like this hyphenated name, from MSR, I think she was an intern there. Anyway, so it's on like occupation classification, and so they used like names as a way to get at like the biases, and like then they had like an unsupervised way of like figuring out like groups of, they did clustering on like how certain names like cluster together in like how they bias the prediction, like in that kind of like the activation space. And they showed that like, so there was like some intersectional like biases along some intersectional subgroups that were percolated up by the model. So that I thought was really cool to see where these biases happening, like rather than like going with the preconceived position of like what like you're looking for. But there's, I think more work needs to be done in that space. I think those work definitely belonged in this slides, but they didn't make it. So.
I have a question about bias amplification. Maybe I can just read the literature and find out more, but it was a new term for me. I was wondering, what is the intuition behind the specific models used that are amplifying bias? Why exactly does it happen?
Yeah, so as I can see that in this paper that Vincent is talking about, one thing we know that it creates a bias is because the model always trying to answer the best answer it can find. That means that even the model has like 50% higher a little bit than 50% want to decide this is a male or female, then you would choose that answer. So that one causing some amplification. But later on, we also analyze the posterior distribution, and we still see there are some systematic bias there. And that one, I don't have a very good answer, but I guess because you have a regularization, you have a lot of things in your model trying to simplify things, and those things will also somehow amplify the bias a little bit. Yeah, and we can have a more discussion offline on this.
Yeah, certainly. I think the easiest way I think about it is like when the model sometimes is uncertain, it just goes with whatever is most likely, not based on the evidence, but just based on the statistics, just in order to do well on the data set, because this is the metric you're trying to optimize for. I think a better way might be to find models that deal with uncertainty in a better way than the current models do. Yeah. So that's all I have to say. So I think we have to end it. So if somebody has more questions, you can approach us, maybe here. So we're past the time. Thanks a lot.